Well, hello, I'm Michael, and are you ready to make your products cool, if they weren't already? In this webinar on SolidWorks Flow Simulation, I'm going to cover the project wizard to easily create new analyses, use the project tree to configure our analyses, and use new features to get a more accurate analysis. We're also going to process the results to easily share with our colleagues and get the actual numbers out of the results and not just the pretty pictures. I think this will be too simple for you. Just wait. SolidWorks Flow Simulation has a wide range of applications covering industries such as automotive, aerospace, industrial machinery, heavy equipment, high tech, consumer goods, medical devices, plant and process, building and construction, engineering services, and so on. And with the two add-on modules, we can specialize in a number of disciplines. So for those of you who have been using SolidWorks Flow Simulation looking for some additional functionality, here are two options for you. Our electronic cooling module, as well as the HVAC module, which bolt right onto SolidWorks Flow Simulation for some added functionality. And I'll be using some of this today. But also, did you know that SolidWorks Flow Simulation meets all of the requirements of Annex A of ISO 10211. So for those of you in building construction, you'll have an easy time using flow simulation to analyze heat loss from a building and analyzing the risk of condensation. All right, let's get to work. I'm an engineer. I'm showing up for my job today. I don't know what's coming at me. So what can I do? Well, since we're using SolidWorks, we have a tool called SolidWorks PDM. When I log into this tool, I receive a notification. This notification is coming from my manager, Dave, telling me that, hey, I need to optimize the fins for a heat pipe. Temperature is not to exceed 70 degrees for the chip. Okay, well, there's the assembly. Let's take a look and find out what's going on here. So here's my design. Fantastic. Let's go ahead and open it up and start taking a look. So I can see for this model, right, I already have a lot of the geometry already created from engineering. We have a PAPS fan. We have a heat sink. And also this heat pipe. And also some fins that are going on here. And I actually have a big problem. I haven't set up an analysis like this before. Specifically when we have this two-resistor component that's in there, the semiconductor, and also this heat pipe. Now, I haven't gotten into this before, so what do we do when we run into a problem like this? Well, we look for examples. So I'll come back to this assembly a little bit later. Let's come back to that PDM tool, because I know one thing that's new to me is that two-resistor model. So let me open up my search, and I'll look for just text that contains two-resistor. This takes a look at the data within my company, and I can see that, hey, I do have two projects here that contain that two-resistor. Fantastic. Well, one of which is, hey, that new project 14 that we're working on. If we take a look at that other one, maybe this was one that was already run. So let's go ahead and browse right to it. And sure enough, I can see some of the keywords that were used here for that two-resistor. There's a heat sink. There's some fans in here. All right, let's take a look at some of this data and see what I can learn. So we'll go ahead and open up this assembly. And actually, yeah, this one looks more complex than the one I was running earlier, the one I need to set up a study for. So hopefully we'll be able to learn some things here. In reviewing this, right, with SolidWorks Flow Simulation integrated right into SolidWorks on the left-hand side, I can see the multiple projects that I have. And sure enough, they're associated to different configurations. So in this first one, we do have this internal fans. We have one for external fans. And also we have another one with external fans with a different heat sink. So we have a pin heatsink. Well, yeah, and it looks like they were trying to optimize this analysis, trying to find the best configuration. Great application for SolidWorks Flow Simulation. But how does this help me? Well, I know in that other model, I'm going to need to create a new study. Now, I've been using SolidWorks Flow Simulation for a number of years. And one of my favorite tools to create a new study, and actually I see this commonly used in the SolidWorks Flow Simulation user base, is consistently using the project wizard. So going to our flow simulation menu, we can go to wizard to start setting up this analysis. Give it a project name, which configuration we're using, what units we're using, the type of analysis. So for something like this, right, I would think that we would have heat conduction inside solids. Keep in mind, this is just walking us through a number of steps as we go along. So for radiation, time-dependent, gravity, rotation, those don't apply here. I know we have some fans, but we do have some fan curves that we will be able to apply. We can define our default fluid, default material. Again, just walking us through a lot of these standard questions that should be applied when we create a SolidWorks Flow Simulation study. And lastly, we have our result resolution. Now, when we create a project, this slider does a lot for us in terms of some of the advanced options. And in this case, right, I've gone through the steps of creating a new project. That's not what I want to do here. I want to find out, well, how did that other user create the project for this internal fan study? So I can't use the wizard for this. The wizard is just for creating new studies. So how do I access the same information from a study that's already been created? Well, it's a right-click away. So inside that study tree, I can right-click on input data and go to some of these options, right, for general studies. And here's where we see that common navigator that we saw in the wizard. So if we do need to make any modifications here, this is where we can go, but also to review how this other study was set up. So very good, this one was using air. The default material here was the typical chip array. And this is actually one of the IC expansions inside the electronics cooling module with flow simulation. And also our initial conditions. But there are some other options there that we saw in the wizard, one of which can be controlled by initial mesh. Now this looks a little bit different. I can tell that the user that set this other study up did not use the automatic settings. And sure enough, if I turn on automatic settings, that looks familiar to the wizard that we saw. Of course, in that wizard, we can turn off automatic settings as well so that we can define a certain number of cells in a given direction and even have control intervals to really refine a mesh in a given area. Especially if we do have small features, how much refinement are we applying to those areas can be controlled with these sliders. Also, if we want to refine all cells or control the narrow channel refinement, and sure enough, we're doing that here. So this has been very helpful. Again, I'll plan on using that project wizard to create my new study, and now using the input data from the old study, I have a better idea of what I want to do here. Awesome. So this gives me enough information to create my new project. But what am I going to do here to set up this study? Now, let's review a couple things that you may already know, right? Specifically with this electronics assembly, this enclosure here. We do have multiple materials applied. Keep in mind, in that project wizard, we applied a global material. If anything is different from that, we do need to go in and specify those individual bodies. So we have our aluminum, our plastics, and our other materials for our other components in the design. Of course, if I needed to add additional materials here for components that are still using that default material, it's a right-click away. Also, if that material was already defined in SolidWorks, I can import it directly from the model. Pretty easy. Of course, the air needs to come in and come out of this system, so we do have some environment pressure openings. But in real life, what happens here, this is more of a perforated plates, right? There's screens here, there are holes in this geometry. Inside the SolidWorks geometry, though, we do not have these holes. We've actually simplified this. However, we still need the boundary condition. Skip a couple things here and come down to these perforated plates. This is another engineering library that we can use inside Flow Simulation to account for that specific geometry where we have those perforations in the geometry that are not modeled inside SolidWorks. So in my new study, right, that my manager has given me, I know I have a couple fans, and we have expanded this fan database inside the electronics cooling module to include a lot of manufacturers. Of course, if you do have maybe a fan that you've developed yourself or from a different manufacturer that's not in here, you can come in and create your own and define these fan curves. Awesome. So I'll plan on using that for my new project. Of course, we'll have some heat sources, very straightforward. Of course, with heat sources, we can do surface sources, volume sources, and apply these to the respective bodies. So if that's a fixed temperature or a given watt heat generation rate. But taking a look a little bit further, there's some additional options here that we'll want to use in our new study. One of which is for that CPU, right, for the superconductor, or the semiconductor. So for this case, we will use the two-resistor model with our electronics cooling package. This makes it really easy to define and accurately solve this analysis in a simplified state. So taking a look at the property manager here, I don't have a lot of options, right? We just specify the case and the junction for these two components of that chip. And then what component is it? What are the resistance values? Again, these are available, many of which out of the box, or you can create your own, like I mentioned earlier in our engineering database. So our resistance values are defined there. We define our heat source, and what's powerful here is in terms of the boundary condition that this also applies, it insulates the sides of this chip so that the heat flows up and down into the board and into the heat sink. Really making it easy to set this up. Also, we have some PCBs defined, and again with the electronics cooling module, we have a PCB generator to help accurately define and create any PCBs that you may use and want to analyze. Lastly, right in this project tree, we have a number of goals specified. Right, this is where we want to create and actually tell Flow Simulation what we're most interested in. So, for instance, the temperature of the RAM and our other electronic components, so we can monitor that maximum temperature. And this is critical, right? My manager told me I need to make sure the maximum temperature is about 70 or below. So I'll make sure I define a goal there. Awesome. So we've been able to use SolidWorks Flow Simulation in this project tree to help set up this analysis. So I'll use this information to create and configure my new study. But wait, I have a challenge here, right? I have a heat pipe in that new analysis, and I don't see a heat pipe in this project tree. Well, there's two ways to approach this. One is to go to your Flow Simulation menu, go to Insert, and find the heat pipe option. Notice there's a couple other options here that don't show up in my analysis tree, like electrical condition for that joule heating and thermal joint. Now, if I create one here, it will automatically add that node to my analysis tree. The other way to go about this is to right-click on your input data folder, right-click on the project folder and choose Customize Tree. Here's where you can turn on and off these nodes for input data and results. So if I want to see heat pipes, I can turn heat pipes on there, scrolling down in my tree. Now I have that heat pipes node where I can just right click and start creating my heat pipes. Very easy. Awesome. So I'm pretty confident that we can set up our new study. Now how are we going to process the results? Because we're going to need to do some optimization and compare a couple different ideas. Well, it looks like that's already been done here as well with this study. And SolidWorks Flow Simulation, again, makes this easy. So we can load our results when we're ready. And then start getting into results for our cut plots, surfaces, isosurfaces, etc. So taking a look at some of these, this makes it not only really interesting to look at, but very powerful and effective to communicate the behavior of this flow. So again, with these recirculating fans, we can highlight and identify where these areas of overheating may occur. I can grab on the arrow here to slide this through the assembly to better visualize the behavior of that flow. But we can do other things. For instance, again, I know in our new analysis that we're going to create, we're interested in the maximum temperature of the chip. So we can do something similar here, creating surface plots to visualize the surface temperature of that heat sink. So of course, the coolest side is on that leading edge closest to the fans, heating up as we get further away. We can also visualize the location of the flow for a given temperature. Now, we can modify this on the fly by changing the value. So as we get hotter, we can see that wave get closer. But why am I not seeing that update? This is where you can turn on the detailed preview. So this actually updates the plot while you're modifying it. Very powerful. And really makes it easy to get that plot that you're after. So I can clearly identify the cooler regions in my model to the hotter. So we've been able to generate some very colorful pictures, and doing one better here is using flow trajectories. So we can actually visualize the behavior of that flow. And we can play this to really make it crystal clear where this flow is going, where it's speeding up, where it's slowing down. So in this case, we're taking a look at the velocity. But of course, we can edit this to instead show the colors being the velocity. Well, why don't we show the temperature? So here's in the analysis where we can see we're going through the heat sink, those fins. That's where we're starting to heat up. Also, as soon as we get closer to the ram, some of these flow trajectories are getting a little bit hotter. So all very good, but again, let's get some numbers out of this. I want to know the maximum temperature of some of these components. So this is where we can actually compare some of our studies to the other designs. Right, and taking a look again at some of these other configurations with the fans outside, and again, the fans outside, external fans, and a pin heat sink, how do these all compare? Well, once I have a plot that I'm interested in, for instance, what I want to show here is this top cut plot. And actually looking at this, I can tell some of my geometry is in the way. So again, we can use the flow simulation tool to globally control the transparency of our geometry. So when we go to export and compare these results, it's a click away. So I can right click on results, compare, and choose for my active scene and the memory chips across all studies. I can do a side-by-side comparison and open these results up. So as you can see, the external fans looks to be the coolest design. But of course, what about the numbers? Again, this is where we can compare, for instance, our main chip, the external fans is the coolest, sure enough, based on our numbers. Of course, how about the memory? Well, as you can see, this varies between the different memory chips. But in that external fan study, that's where we can see, yeah, this looks to be the coolest design. The external fins with the fin heatsink is pretty cool, but not for that main chip. So awesome. This is how that user was able to figure out the best design for this analysis, utilizing that compare tool and understanding the behavior of the flow, utilizing those cut plots, surface plots, etc. So we've been able to find our answer. We know how we're going to get into flow simulation and create this new project. So let's go ahead and open that study back up. So again, we can utilize SolidWorks configurations to get started. So we have a very rough analysis here that we'll create a new study for. So again, this is kind of the initial, the cheapest heatsink, or the number of fins that we would make. The geometry has already been created. We just need to associate it with flow simulation. So again, I'll use that wizard. Specifying our properties. For instance, in this case, I may be interested in having Celsius for our temperature. And keep in mind, if you do want to create new and save these custom unit systems, you can. So we will have heat conduction in solids. You know, one option over here on the left-hand side is, since there isn't a lot of airflow going on, I think I want to account for that natural convection. So I will turn on gravity. Notice this is represented graphically in that 3D model at the same time. Internal analysis, I think we're ready to continue on. Now, actually, one thing I mentioned earlier with this study is I could turn on rotation. And traditionally, we've had just that averaging type for the rotation. But new in SolidWorks 2015, we have this new sliding mesh to more accurately represent some of this asymmetrical flow. But in this case, right, we don't have rotation and we're not doing type dependency here. So we'll continue on. Specify our fluid, our expanded database with the electronics cooling module, our typical chip array, default parameters, initial conditions, and our result resolution, and we're ready to continue on. Now, using the power of television, I've already gone through this and created a separate study already. So this has been for our heat pipe with 10 fins. So I've gone through the additional steps like we saw earlier for defining some of these other solid materials. We've created the environment pressure like we saw in the other study, but in this case, again, rather than solving for this fan, we're optimizing this analysis and simplifying it by utilizing an inlet flow. Because again, we already have a fan curve defined here. We know the amount of flow coming out. It's been heavily tested. We'll just define this with a boundary condition. This will save a lot of time for that calculation. But we need to do a little bit more work here to fully define this study. Now, one thing that we talked about earlier was that two-resistor component. Well, sure enough, we're going to apply that here. So we have two bodies, right? One for the case, one for the junction, and we've defined the component for that two-resistor model. Keep in mind, if you need to modify or create a new one, the button is right here to do so. And based on our manufacturer specifications, we've specified our heat source. And how is this going to interact? How is that two-resistor component going to interact with the PCB? And how is it going to interact with that heat sink that's going to the heat pipe? Well, we have some bonding, we have some bonding material between these components, right, to decrease the resistance and allow the heat to be absorbed more readily. So to define this, we have defined unique contact resistances. So all we specify here is a given face and the resistance associated on that face. So we've also done this for the interface between the two resistor components and the heatsink with that bonding material. And the last part here is one step you can take to control how that heatsink is going to, or that heat pipe is going to behave. And this is where we've defined a contact resistance to the external faces that are not, either radiating or not having any heat transfer go off of them. Right? So all the heat transfer is coming in into that sink and out of our fan area. So we've defined a contact resistance here with infinite resistance. But that's not all we have to do with this heat pipe. Like I mentioned earlier, we can create a new heat pipe. And you can take a look at the help here. It's actually very straightforward to create, right? And often enough, you can take a look at the manufacturer of this heat pipe, as there's lots of different types of how this can be created, which means that there are variable types of the effective thermal resistance for that heat pipe. But what we specify here is the interface, where we have heat coming in, right, associated to that heat sink, and where the heat is going out at our fins. Lastly, we've specified goals to help analyze and converge on our results, right? The one that we're really interested in is that volume goal for the chip, so we have maximum temperature for that solid. So we can solve the analysis and start taking a peek at some of our results. So I can take a look at this with our surface plots, and sure enough, I can see like the maximum temperature is about 90. So this is a problem, and if I want to, I can start communicating this with other folks. I can save this out as images or as e-drawings as well. This really makes it easy to allow other folks to open this up, rotate the model around, and see the exact behavior of what's going on here. So sure enough, we need to take more heat away at those fins. Likewise, we've been able to do this graphically, but how about the numerics? Well, we can edit the definition for our volume parameters here, add that temperature for the solid, and show it, and see our maximum temperature of about 90. Now, continuing on here, I can manually create these other configurations, but do I have to manually recreate all of this project work? The answer is no. We can maintain it. Fantastic. So right-click on the top of your analysis tree, and we can clone the project. And we can clone this out to either new configurations or other configurations as we wish. So I've already done this for our heat pipe with 50 fins. Think it's too much? Well, let's take a look. So we'll go ahead and load those results for our 50 fin study and take a look at our results. And sure enough, what we find is our temperature is far lower. We're at 63. So we have some very good heat transfer going on here, but maybe too much. Maybe all those fins is going to result in a higher cost. So can we optimize the analysis? Well, again, I could keep going on and manually define this and create new studies, or I can actually do one better. With Flow Simulation, there is an optimization routine built right into the solver. So going into our menu, we can create a new parametric study where we define input variables and our output parameters, what we're after. We can do this for multiple what-if scenarios or goal optimization like we're interested in here. Now I've already created this, but essentially I'm linking to the instance for the patterns for those fins. We're ranging from 10 to 50. Our criteria here is that volume goal that we specified in Flow Simulation, where our target is 70. And in terms of the refinement here, yeah, we'll be plus or minus 1 degree. We can list any other output parameters that we want to define, and then run through the scenario, specify a maximum number of calculations, so we can let this run overnight, over the weekend, and come back and view our results. So in this case, what we've been able to do is optimize this to about 29 fins. And again, taking a look at our cut plots and our volume goals, we can really make it easy to understand and confirm that we're meeting our new design requirements. Awesome. So we've been able to use the power of SolidWorks Flow Simulation, the power of the wizard to create new studies. We've taken a look at how to go back in and modify and update what was defined in the wizard. We've utilized the analysis tree to add additional nodes to account for additional components and geometries and physics that we want to account for. And utilizing the power of the post-processing tools of SolidWorks Flow Simulation to communicate this to non-SolidWorks users, as well as to creating some of these reports. And as you take a look there, as you get through the interface, notice there are a lot of buttons to export this information right to Microsoft Excel. So with this new design, I think we have our final design. We have our new configuration created. So right from SolidWorks, utilizing our PDM, I can tell my manager that the analysis is complete. So I can even give him a little heads up there that use the final design configuration. And I'll notify my manager, Dave. Awesome. So that's going back to under editing. My manager will be defined, and I can go home for the day. So thank you all for your attention. Hopefully you found some new information here using SolidWorks Flow Simulation, and especially some of the additional modules for electronics cooling and HVAC. If you have any questions, and if you're wanting to make your products a little bit more cool, visit qintegration.com. Thank you, and have a great day.